In a randomized controlled trial in Kenya, insecticide-treated bed nets were tested as a way to reduce malaria. Among 343 infants using bed nets, 15 developed malaria. And among 294 infants not using bed nets, 27 developed malaria. So, what's going on in this chapter that's different is we are working with two different samples, one from each of two different populations. So far it's always been one population. Now we're working with two. So that's the whole point of chapter 9. So we're going to do all the same stuff as before, except for two populations. So, we'll work with the parameter p for proportion. We'll work with mu. We'll work with sigma. Okay. But there'll be two populations. So it'll be like p1, p2, mu1, mu2, sigma1, sigma2, that kind of thing. Okay. Whoops. Okay. So we wanted to use a zero point zero 0.01 significance level to test the claim that the incidence of malaria is lower for infants using bed nets. All right, well, test the claim. That tells me H null hypothesis, H1 alternative hypothesis. Okay. Now, the first the first sample mentioned is the 343, so we're going to call that population 1. Okay. And the second sample mentioned is the 294. We'll call that population 2. Okay. And and so it says we want to use a zero point 0.01 significance level to test the claim that the incidence of malaria is lower for infants using bed nets. Okay, the bed net kids, they're the 343. That's population 1. So we're saying malaria, the percentage of kids who got malaria was lower for population number 1. So population 1 had a lower proportion or percentage of, um, of malaria, except, wait a minute, this doesn't go there. That goes down there. The equal sign needs to be in H sub 0. Okay, so those are our hypotheses. Okay. Okay, so now it's time to run this thing um, through the calculator. Okay, so I'm going to go stat over to tests, and we're looking for a two proportion z-test, two proportions. Before in chapter 8 it was one proportion, but now we got two. All right. So our population number 1, we said that was the first one mentioned. So there were 15 successful malaria cases. I know it seems really brutal to say, hey, success is getting malaria. Great job, everybody. And then that was out of 343. And in the other population, or in the other sample from the other population, 27 successfully got malaria out of 294. Okay. And we're going to do the less than sign. We see that from H1, the alternative hypothesis. We'll go down and hit calculate. And we get this. Okay. So the p-value um, is going to be 0.0074. Okay, so we have that. Okay, and our alpha value is 0.01, which is greater than the p-value. Therefore, we're going to go with H1, and that'll be just so wonderful. And so we can say, um, let's see, at the zero point zero 0.01 um, significance level, um, let's see, there is sufficient evidence to reject H sub O. Okay. Therefore, the bed nets appear to make a difference in avoiding malaria. Okay, so you could have something like that. Okay, now I did neglect to write part of the problem I wanted to include. Okay, that was part A. Yeah, okay. So um, now we need a little something extra. Okay, now I'm gonna give you that other part. Actually, you know what? I think I'll just do it over here because um, I'm not using that space. Let me move that over. And you know what? I should probably just pause this. That would be smart. Okay. Now we have test the claim by constructing an appropriate confidence interval. So now we're going to examine the same claim, but with a confidence interval. Hmm. But you say, wait a minute, I thought confidence intervals were used for testing or for estimating parameters. Well, they definitely are. But yeah, you can also get away with constructing a confidence interval sometimes for it. So here's how it's going to go. Okay. We're going to go to stat over and down to what are we looking for? Uh, okay, two prop z int. Okay, two proportion z interval, as in confidence interval. Okay, now here's the cool thing on this calculator. Notice all the data is already there. Okay, it's just going to grab what we just did and say, well, let's just keep that for the next one, and that'll be cool. Okay, so, but there is one little trick here. Okay. There is one little thing here that I do need to point out to you. Okay. Um, when H1 contains the not equal sign, um, the level of confidence equals 1 minus alpha. Okay, where alpha is 0.01, the significance level for the hypothesis test. So I'm taught, yeah, okay. Um, Otherwise, the level of confidence equals 1 minus 2 times alpha. Okay, so that is a little something that you'll need in this section. So, and again, just to remind you, the level of confidence that, that's what we worked with for confidence intervals. And so we need to know what is our confidence level for this. All right. Well, does H1 contain the not equal sign? No, it does not. Okay. If it did, then we would just say, well, 1 minus alpha, boom, 99%, that's it. Okay. But it doesn't contain the not equal sign. So it's going to be 1 minus 2 times alpha. So our level of confidence will be 1 minus 2 times alpha. Okay, which is 0.98. Certainly close to 0.99, but not the same thing. Oh, I gotta click on that. Okay. Whoops, too far. Ah, come on. Ah, what did I do? Oh my goodness. Okay, hit the wrong button. All right. So 0.98. So that's what I'm gonna do. And so then we get a confidence interval of negative 0.095 to so negative 9.5%. Okay. And basically what we're estimating is P1 minus P2 up to negative 0.13%. Now, here's what you need to be aware of with this. Okay, when you're examining a confidence interval to or using confidence interval to examine a hypothesis test. The question is, does this interval contain zero? Well, no. I mean, they're both negative. They're both the same sign. So no, it does not contain zero. Oh, okay. So this confidence interval suggests that P1 minus P2 does not contain zero. Oh, so if I add P2 to both sides, and you're not going to have to actually do this. I'm just explaining, what's going on. So then that we come to the conclusion, oh, P1 and P2 are not the same thing. Therefore, there is a significant difference in the proportions of population one and population two. Therefore, because since there is a significant difference, we the confidence interval in this case also says reject HO. Okay, and we come to the same conclusion. Sometimes you don't come to the same conclusion, but often you do. But that's kind of the idea right now, right there. So all you're going to have to do is get the confidence interval and then just say, does the confidence interval contain zero? If it does, oh, then I'm going to fail to reject HO. Okay, but if it does not contain zero, then I will reject HO. So that's the idea with that. Let's move on. Data set 11 from the back of the textbook includes lengths of times in seconds of tobacco use shown in animated children's movies. For the Disney movies, N equals 33. So they looked at 33 Disney animated children's movies. The mean tobacco use is 61.6 seconds, and the standard deviation is 118.8 seconds. For the other children's movies that are the non-Disney, they looked at 17 movies with a mean of 49.3 seconds and a standard deviation of 69.3 seconds. Okay, so use a zero point zero 0.01, or I'm sorry, zero point zero 0.05 significance level to test the claim that Disney animated children movies and other animated children's movies have the same mean time showing tobacco use. So once again, we're working with two different populations here. Okay. And I tried to shrink this stuff down. I didn't see how to do it, and I was in a hurry. Okay, so um, and we're talking about, where was it? The mean times. So we know we're going to be comparing two means. Okay. So I'm going to call it mu sub Disney and mu sub other. Mean of Disney, mean of other. Okay. And I'm putting Disney first because that's the first one that's mentioned. All right, so then it says, okay, so we want to test the claim for same mean time, which means equal. Equal goes in HO. And so that's all they give us. Therefore, this one must be not equal. The negation of equality. Okay, so let's get to the calculator here, shall we? Okay, so we'll go stat, tests, and then I want so when we were testing for mean before, it was a t-test. So now we got two samples, so two sample t-test. All right. We have the stats. If we had the data, it would be an L1 and L2, as you can see right there. But we've got the stats. They've clearly given that to us. So for the first population, that'd be Disney. The mean is 61.6 seconds, and the standard deviation is 118.8, and the sample size is 33. All right, let's move on to non-Disney, the others. So that would be 49.3 second mean, and a standard deviation of 69.3, and a sample size of 17. We're going to pick not equal, and you're just going to leave pooled on no, and that's fine. And I mean, you can look at it and say, all right, does it look like, they're equal, they're not equal? I mean, does it look like there's enough evidence to suggest that they're not equal? Well, there's something to think about. Let's calculate. All right. So we've got that. The p-value is 0.64. Okay, so by now you realize that, okay, that's a very large p-value. It is, nowhere near alpha. And alpha is, did I include that? I meant to. Yeah, I did. Okay, so alpha is 0.05. Okay, so our p-value is definitely greater than alpha. So we're going to go with HO. We will fail to reject fail to reject the null hypothesis. Okay. So I should probably write that down. Okay. So I will say, I'm going to do some abbreviating. So at the 0.05 significance level, there is insufficient evidence to reject the null hypothesis, HO. Therefore, um, oh boy, my eyesight's clearly not what it was. Um, so we don't have enough evidence to reject it. So I mean, yeah, again, the two means are not likely to be identical, but we don't have enough evidence. I mean, part of it probably is the small sample sizes. That's probably a big part of it right there. Um, anyway, so we've got that. Now, what about part B? Okay, now let's make a confidence interval to explore that same explore that same concept, that same test. Okay, so we're going to go back to stat over, and a instead of doing t interval, we want to do two sample. Where is it? It's somewhere around here. Two sample t interval. There it is. Okay, so we're going to go there, and like before, hey, everything's already loaded for us. That's pretty cool. I'm digging that. Now remember, earlier on in this video, um, we talked about the confidence level. Okay, so remember, if H1 contains the not equal sign, which it does this time, then the level of confidence is just going to be 1 minus alpha. Okay, 1 minus the 0.05. So 95%. Okay, we'll calculate. And this time we get, oh, hang on, I gotta click on that. Oh, poop. I didn't click on it properly. Okay, so this time the confidence interval does contain 0. Therefore, it's possible that the two means could be equal to each other. Therefore, the confidence interval also suggests that, hey, we do not have enough evidence to reject H sub O. All right. And that is how we do things downtown. Okay, so now it says listed below are heights of fathers and their first sons, Use a 0.05 significance level to test the claim that there is no difference in heights between fathers and their first sons. All right, so first of all, we know we're doing a hypothesis test. So I get that. Now, this time, I mean, yeah, it's true that we are comparing two populations, heights of fathers and heights of their first sons. That is two different populations. That's why it's in this chapter. However, unlike in the last section, in this section, there is a natural way to pair data between the two populations. Okay. Um, and I'm going to show you that data in a moment. I already put it in the calculator. So that's, in fact, I should probably just show that to you now. Okay. So if I go stat enter, there it all is. There's all the data. And let's see. So L1, that's fathers, and L2 is their sons. Okay. So what that means is this is the height of a father, and this is the height of that father's first son. Here's the height of another father, and here's the height of that same father's first son. Therefore, there is a natural way of pairing. Okay, now if we were saying fathers and sons randomly, then there would not be, and there wouldn't be a natural way to pair them up, and therefore it would be a problem like we just did in the last section. But when there's a natural way to pair them up, then you pair them up, okay? And because that gives us additional information, okay? That is valid. Okay, so let's go back to our hypotheses. So when there's a natural way of pairing it up on the means, then mu sub d is going to be your parameter, okay? And what that stands for is the mean difference, or the difference of the means, the difference of the mean of this population and this population, okay? And so it could be zero, but they say, hey, no difference. Okay, that means that the difference of their means, of their mean heights, is zero, which means this one has to be not equal. All right. Now, I know you're thinking, wait, there are two populations. You've only got one variable, one parameter here. Well, that's okay, because since there's a natural way to pair them up, I can go up to L3 and I can say second one and grab list one, and then minus second two and grab list two and hit enter. And then what that has done, what the calculator has done is it has said, okay, I'll do 72 minus 73 is -1. 66 minus 68 is -2. I mean, you could just type them all out real quick, but this is a little faster and easier. Okay. And so it is doing it, it's looking at all that. And so now what we're going to do is we're going to use L3 only. Okay, we no longer need L1 and L2. We don't need them. We're going to use L3 only in our hypothesis test and in our subsequent confidence interval. Okay, so that is what's going down. And again, we're interested in, do those differences appear to have, do the differences seem to be about zero? Okay, well, some of them are negative and some are positive, and some are zero. So I don't know. It looks like it's everything's hovering around zero. So I think we're probably going to end up with that the difference in the heights of fathers and their first sons is probably going to be around zero, which isn't terribly surprising because it's their own child, same gender. Okay, so here's what we're going to do to wrap it up. We're going to go to stat and then over, and then we're doing a test for a mean, but we're only looking at one list of data, so t-test is going to do it. So we're not going to do two sample t-test, just t-test. Okay, we go there. We've got the data in L3, so do second 3 to get the L3 there. Our H1 is not equal, so we got that. And then we've got this. Okay, so the p-value is super high, super high. Okay, alpha is typical 0.05, something like that. And so clearly the p-value is way higher. I mean, that's just about as high as you can get. 1 is as high as you can get. So we'll say, hey, at the 0.05 level of significance, there is insufficient evidence to reject HO. So maybe the difference in their heights is 0, maybe not. Maybe first sons are the same height as their dads, maybe not. But there's definitely not evidence to reject HO. So we're going to go with HO. All right. Now we need to construct a confidence interval. Okay, so let's see what the confidence interval tells us. Okay, so like I said, the confidence interval is going to be based on our data in L3. So, okay, so that's cool. Excuse me. So I'm going to go to stat over here. And just as I did t-test, because I was working with one set of data, one list of data, for the interval, I am not going to do two sample t interval. I'm going to do t interval, okay, for one single list. And the data is in L3. And because we have the not equal sign in the in H1, our confidence level is going to be just 95%. Again, if we had like a less than or a greater than there, then we would say, oh, 1 minus 2 times 0.05, and that's 90%. But, that wasn't the case. Okay. So, um, we got that. Oh, I got to click there. Boom. Chicken soup. Okay. And I got this. And so there's the confidence interval associated with this situation. So negative 1.3 inches um, up to 1.4 inches. Okay. 6 inches. I know, I had an elf moment there. Okay, so there's the confidence interval, and once again, the main thing we're interested in, does this interval contain zero or not? Okay, it does contain zero, suggesting that mu sub d could equal zero. And remember, mu sub d, that is the mean height of the fathers minus the mean height of the sons. Okay, or another, and so if that difference could equal zero, then that would suggest that it's possible that the mean height of the fathers could equal the mean height of the sons, and therefore, just like with the hypothesis test, the confidence interval suggests, hey, HO is probably the way to go. There is insufficient evidence to reject the claim that the heights of fathers and the heights of their first sons are significantly different. Okay, so that is how that one goes. Okay, I gotta go. Pizza just came out of the oven. I'll come back and finish the video in a few minutes. Okay, this one's a little bit longer, as you can see. So, data set 12 in the back of the textbook includes cotinine levels measured in a group of smokers. Okay, so you've got statistics for smokers. Hope you can't hear the background noise. My family's being pretty loud. And a group of, okay, why is that Greg Borman still there? That is dumb. Okay. And a group of non-smokers not exposed to tobacco smoke. Sorry about that. I'm not sure what's up with that. Oh, okay. Well, I don't know why, but that seemed to fix it. Okay. I don't know what's going on. Okay. And then, so here's all the statistics for the non-smokers who are not exposed to tobacco. Okay, so use a 0.05 significance level to test the claim that the variation of cotinine smokers in smokers is greater than the variation of cotinine in non-smokers who are not exposed to tobacco smoke. So clearly, we're having a hypothesis test. Okay, I know, not a lot of room on this page, but oh well, doing the best I can. So, um, and we are comparing their not their means, but their variation. Okay, so smokers, they were listed first, so that's going to be population number one. Non-smokers, that was listed second, that'll be population number two. All right, so we're saying, is the amount of variation the same? Or is the cotinine in smokers, that's population one, is it greater than the variation in the non-smokers who are not exposed to tobacco smoke? Okay, so that's our thing right there. Okay, here we go. And we're going to go to stat over. And for when you are testing two the variation, comparing the variation between two different populations, we use two-SAMP-F test. Okay, so we've got the stats, so we'll do that. So for the first population, the sample standard deviation is 119.5, and the sample size is 40. Looks like we don't even need the sample means. Case for population number 2, the sample standard deviation is 62.53, and the sample size is 40, I think. Wait, did I read that right? Yeah, 40. Okay, and if I look at my H1, my alternative hypothesis, it has a greater than sign, so I'll select that. And then I'm going to go calculate. Okay, so we've got a p-value. I'm going to go over here. P-value equal to 0.0000. It rounds off to 5, which is certainly less than alpha, whatever alpha is. In this case, it is 0.05. Okay, so we're gonna go with H1, and we're gonna say, hey, with I don't have a lot of room, so I'm just gonna say it out loud. So at the 0.05 level of significance, there is sufficient evidence to reject the claim that that the amount of variation in smokers with cotinine levels and the amount of variation of cotinine levels in non-smokers who are not exposed to tobacco is just not the same. Okay, again, we're not saying that the amount, the mean amount, this has nothing to do with mean. We're not saying that this test does not say that smokers have more cotinine. Okay, they probably do, but this test does not test for that. This test just says, well, there appears to be more variation in the amount of cotinine in smokers, okay, than there is in non-smokers who are not exposed to tobacco. Okay, let's go to part B. The 40 cotinine measurements from the non-smoking group consist of these values: 1, 1, 90, 244, 309, and then 0 a whole bunch of times. Okay, 35 times. Does this sample appear to be from a normally distributed population? So it's going to be 0, 0, blah, 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 35 times, 35 zeros, and then a 1, and a 1, and a 90, and a 244, and a 309, E-I-E-I-O. Okay, so does that appear to be from a normally distributed population? No, not at all. If you graph that, the graph, starts out low, 0, 0, 0, 0, 0, and then finally at the very end, after you've done 35 numbers, it pops up to 1, and then it pops up really high to 90, 244, 309. And so it looks, something like this. So it's definitely not normally distributed. Okay, so how does that affect what is going on? Well, since the sample is not from a normally distributed population as required, the results in part A are highly questionable. So we did some calculations in part A, but this isn't based on a normally distributed population, and therefore the results are questionable. Okay, so that's something to be thinking about. Anyway, that should do it. Okay.